Hey guys, today we are starting a new unit on waves. But before we kind of dive into that, I just want to go over a couple of quick things about energy. So last Friday, I assigned sort of like a makeup day. So this was specifically for if I had some people who hadn't quite yet turned in their LOL chart practice, either from day 8 or day 9. I've emailed you about it if you were missing it. This was kind of a chance to, if you wanted to make corrections, since that's an assisted grade. Assisted grades you can always just make edits to and corrections to sort of help boost your grade, bring it up. Or if you didn't do as well on the quiz as you would have thought, the energy bar graph quiz from Monday and Tuesday, then you had a chance to retake it then. Just because this assignment is now over with doesn't mean that you can't either A, retake the energy quiz, or B, improve any of your assisted assignments, of which you should see in Home Access Center, using the comments that I've sort of left for you in order to bring things up. So for instance, if I gave you like an 8 out of 10 on one of your LOL graph assignments because you were just missing one thing, change that one thing and I will change your grade. Okay? So easy little ways to kind of boost things up if you need to. On that note, we're going to go ahead and look at today's assignment, and then I'm going to go into what this unit is about first. So today's assignment is to watch this video and then fill out this exit ticket, and then we're going to be taking kind of like a notes version of waves. It mostly involves a lot of drawing, which is the cool part about waves. There's lots of diagrams. So today we're just going to be doing our diagram. Your exit ticket, I'm actually kind of interested about what sort of, we only have so many weeks left, and I know that we aren't going to really go into the same level of detail or the same level of experiments as we would have if we were in class together. Therefore, I'd like to kind of try to get an idea of what sorts of either really applied or really interesting things in this unit that you guys want to learn about or talk about, or if we need to do more kind of like pick your own assignments, then this question just helps sort of guide that. And then finally, again, the semester is kind of winding down. I've been hearing from some students during the Google Meets that I host every day at 2 to 2:30 about sort of how their workloads are going for this class or how it's going for your other classes. So I would just like some feedback about both of those things here, about how you're doing, how you're finding specifically our class, and maybe how our class is relating to your workloads in other class. So I want to make sure that you guys are, like learning the stuff, but also, are you okay? Like, just let me know, okay? So on that note, fill out that for attendance, please. You can do that anytime during the 2 days, and I can go back, make corrections if needed. But let's look at our assignment. So I'm going to explain what these terms mean in just a second. But today you are just drawing a picture of a transverse wave. Again, I'll explain what a transverse wave is when we look at our notes. And you're going to label it using the vocabulary below. Off to the side, you're going to create a key that has these terms and these definitions. If you'd like to rewrite a definition into sort of your own terminology, or if you want to look it up, I would recommend just if you Google a definition, make sure you put in waves. Some of these words have a slightly different meaning out of context of science. You will be using this picture throughout the unit, which is the next 2 to 3 weeks. You can use whatever you want to. If you want to color a picture, if you want to paint something, that would be super cool. Google Draw, Photoshop, any kind of online source, that's fine, but you can't just Google image. I can do a cross research and I will know. I'll kick it back to you. Anybody can just Google an image. Just make your own. Doesn't have to be good. Doesn't even have to be creative. But it does have to have the terms. And it does have to be by you. You can upload your picture here, or if you'd like to do it as an attachment onto the assignment, that is also fine. All right, so let's go ahead and look at today's lesson. I'll only go through a few of the basics, but this is our PowerPoint slides. They are here for you to refer to throughout the unit. All right, so our presentation today is on waves. I'm gonna hide this real quick. Might take a second to load. There we go. Okay, so number one, I really like waves. Whenever we're first just start learning about these in science, it's really just about the basic vocab. But as you get further into it, you realize, oh my God, I didn't realize that was a wave. There's so many things. So a couple of things. Waves includes all sound waves. So all of sound is a wave, right? So we're looking at this picture here. In fact, everything on this page is a wave, or a form of a wave, or a form of a wave technology. So sound waves are waves. So is light, especially light that plants can use, which provides the basis for our life, right? Other things include electromagnetic waves, other electromagnetic waves like infrared radiation or heat. So this is a mouse on infrared. We have radio waves and also microwaves. The cool thing about microwaves is it's not just something used to heat over Hot Pockets. It also is the basis for all of our modern technology, including laptops, cell phone towers, and TVs. If we didn't have microwaves or we didn't know how to use microwaves, then we wouldn't have those things. If we look at waves in nature, then we could think about the power of tides. We could also think about the destructive power of earthquakes that we're going to learn about. We've also started using waves to use in different medical contexts, such as an x-ray here of a person's chest, or maybe an MRI or a CAT scan. All of those things are applications of waves technology or a way in which waves influence our everyday life. So that was kind of what that first question was about. Which of these things do you guys find really interesting? What things would you like to learn a lot more about? We'll get into it. Okay, so the cool thing about waves, that's kind of confusing, right? Is that even though waves can move really, really fast, the actual things in a wave, like the actual particles maybe, are really just things going up and down, which is weird, right? Like you see something go left to right, and yet everything in it is just going up and down. But to sort of get that idea, I want us to look at this very, very short video. All right, here we have a football game. People doing the wave at Michigan State. It's a little blurry up here, but okay. You see it? Okay. All right. Each person is just standing up until we get to our video. There we go. They're excited. I kind of miss sports. All right. So even though that wave was able to travel the entire length of that stadium, the entire time, every person only did one thing, right? They stood up and they sat back down. So all waves kind of work that same way. Even though they move from place to place, it's really just about something going up or back down, everything going one at a time. So that's what a wave kind of does. But what is a wave? So a wave is a transfer of energy. Matter itself is never transferred, ever. All right, so waves transfer energy. They don't transfer stuff. Most waves are created by some type of vibration. There's a couple of different types of waves that we're going to talk about. There's transverse and longitudinal, which refer to what the shape of the wave looks like. And then all waves are either mechanical or electromagnetic, and that refers to what the wave can move through. Okay, here's a great little guide just to sort of reference that. So what's the difference between these things? Mechanical waves are those that require a medium. So wait, what's a medium? A medium is something that you can travel through. In this case, a gas, a liquid, or a solid. So mechanical waves are just waves that can travel through gases, liquids, or solids. But wait, I hear you ask, I thought that was all there was. Not quite. Electromagnetic waves are waves that don't need a medium, so they can travel just through space, which is a vacuum, which just means that there's not a whole lot out there. There's very little pressure. There's no gas. You're not really running into very many solids. And there's definitely no liquids because it would all be frozen. So examples of mechanical waves include waves on an ocean or sound waves. Sound waves are very big. Cool note about sound waves, they travel pretty fast in the air, but did you know that they actually travel the fastest if you hear them through a liquid or a solid? So as the mediums get denser, then you hear mechanical waves or you experience mechanical waves a little faster. And to sort of think about this, if you've ever been underwater and tried to speak, then you know it sounded kind of funny, right? It probably sounded more amplified. And that's because that sound wave was traveling faster through the water than it would have been if you had put your head up above and shouted it out there. Electromagnetic waves do not need a medium, and they can travel through empty space. Real quick, the ones of which you guys might be familiar with are radio waves, like those we use for radios. Yeah. Microwaves, again, like I said, not just limited to the thing that heats up my toaster strudel. You can also use these for a bunch of different applications, like most of our telecommunications. Infrared, also related to heat. The only part of this spectrum that we can actually see with our eye is visible light. So visible light is red, orange, yellow, green, blue, violet, right? However, lots of animals can kind of see on slightly either sides of this. So some animals can see in infrared. Some animals can see ultraviolet radiation, UV radiation, which is what could give you a sunburn, perhaps. And some animals can only see a few of these colors. So sometimes they're limited. All right, so we have ultraviolet radiation and then X-rays, like what we can use to see if you have a broken bone. And then finally, gamma radiation, which we will probably talk a little bit less about. It does not, however, give you superpowers. So sorry about that. Electromagnetic radiation, I will touch on more later. Just know that light is sort of the opposite of sound. It travels the slowest in solids and the fastest in gases. All right, transverse waves, the thing that you are doing today. The transverse just refers to what it looks like. On this, it talks about looking like a sine or cosine curve or a graph. You might remember this from algebra. However, you can also refer to them how I occasionally refer to them. Transverse waves look like snaky snakes, and longitudinal waves look like slinkies. Easy to remember. On a transverse wave, you're just going to see up and down, up and down, up and down. And there's different parts of a transverse wave. It's important to know these parts because it relates to how much energy that wave can transfer, how it moves, how quickly it moves, and what type of wave it is. It's a lot of information. So today we're basically going to be creating this sort of same design, only besides just labeling these parts, you're also going to write out what those parts are off to the side as a quick reference. So let's just go through them. And actually, I want my woohoo. Okay, so a node, which is this point right here, along this line, is the normal resting position of a wave. Here at this bottommost part, so at the kind of lowest down point that you can see, that is called a trough. The highest point of a wave, right up here, is called a crest. The amplitude tells you how tall a wave is. I was going to try to write out tall, but that's not working very well. All right, whatever. The amplitude of a wave also tells you something about how much energy a wave has. The more amplitude, the more energy you're able to convey. Finally, we have a wavelength, which is also represented with this symbol called lambda that looks kind of like a 5-year-old tried to draw a house and it just didn't go well. The wavelength of a wave is the distance from either one crest to crest or one trough to trough. Now, how do you know how big a wave is? A wave has to be one up and one down cycle. So this right here would be one wave. And then this right here would be two waves, and so on and so forth. So just one hill or one valley would be a half a wave. All right, go back to the clicker. Go back to the eraser. My bad. You figured they would put these in the instructions. It's fine. Okay. Okay, so parts of a transverse wave. Just to recap, crest is the top, trough is the bottom. The wavelength is how wide the parts of the wave are from each other. The amplitude is how tall, and the node is like the resting position, or you could think of it as like 0. And then a couple things. So these two terms refer to how many waves occur in a certain amount of time, and they're sort of flips or inverses of each other. So frequency is how many waves happen per second, and we measure frequency in hertz, which is sometimes abbreviated to Hz. The opposite of that is period. That's, okay, if I had a timer, how long does it take to do one wave? And that's measured in seconds. Most of the time, though, we're going to use frequency, and that's the one that I would like you guys to focus on in this assignment. All right, we're going to pause here. So again, these terms are also listed right here with the definitions. Your assignment is to make a picture of a wave, label it using these terms, make yourself a key off to the side, and then upload a picture of that there. And remember, this can be in different media forms, but it just cannot be a Google image search. All right? And with that, I hope you guys have a great night. Email me if you have any questions or check into office hours, okay?